Oh, guys, so we have already explained what is the extension sort and how mesh sort works. Okay, so now I'm going to explain to you what is the bubble sort algorithm about. All right. So first, I don't really recommend, or I don't really see using this algorithm because it has one of the worst case time complexities. So the time complexity or the average time complexity of this algorithm is polynomial, right? So it's going to be quadratic. But it's kind of, let's say it's kind of similar to insertion sort. So only use it if you really have a small amount of items, all right, in a array. So when we know that, we're going to explain this easily. So bubble sort is really easy to explain. So imagine we have this array, right? We have an array of size 4, and then we have, I don't know, let's say we have 100 here, and then here we have 5, and then here we have 1, and then here we have 33. All right. So how the bubble sort algorithm works? So you simply, all right, it's very simple. You take two consecutive items, all right. So you have to have neighbors, two neighbors, all right, two consecutive items. Once you have two consecutive items, we another thing before continue, I have to say that we work this from left to right, all right, and then we come back again to do the same from left to right. All right, so that's what we're doing here. We're going to left to right. All right, so we're going to do this first on the left side. So we have our neighbors. We have two consecutive items, 105. All right, and now we sort it. We compare it each other. So obviously 5 is less than 100, so it's going to be like this. All right, and then what we do is continue. So we on the other side we have 33 and 1. All right. So now what is the next two pair of neighbors or two pair of consecutive items? Is these two. All right. So we compare these two. So 33 is obviously less than 100, so we put this right here. All right. Then we have 5 on this side, and then we have 1. All right. And then we do the same. Two consecutive items. So it's going to be 101. We compare each other. And then what we have left is 5, right? 5, 33, 1, and 100. All right. So this is almost sorted. So we do one iteration, all right, from left to right. So we do, if it's not sorted, we do again another iteration basically. So we're going to do again left to right. So we started here, we compare these two. As these two are sorted, it stay the same, and then we compare these two. So if these two are not sorted, so what we're going to do is 5, 1, 33, and then 100. All right. So we have almost sorted. We continue doing this. So this is sorted, so it ends up there. And then this is another iteration, and we do again another iteration from left to right. So we compare these two. All right. So this is another one sorted. So it's going to be 1, 5, 33, and 100. All right. And then we continue doing 5, 33 are sorted, and then 33, 100 are sorted. So at the end, this is how the array is ordered. All right. So we basically do iteration of two neighbors, of two consecutive items from left to right. We order, and then we do again another iteration if it's not sorted. That's basically bubble sort. All right. So as I said, it has a average and worst case scenario of O or big O of a quadratic function, and the best scenario is that if it's already sorted. So imagine we have this as an input, so this is sorted already, and you would only do this and then this, and then this. All right. So you're going to do item by item. So the best case scenario is that you do big O, right? That you do big O of M. In other words, linear time complexity. So this algorithm, it has a space complexity. All right, it has a space complexity of 1. As you can see, it's only using its own arrays, not using extra memory. So that's why the space complexity is 1. And then this algorithm is in place. All right, it's an in place algorithm. All right, and then it is also stable. All right, it is also stable. So yeah, that's it, guys. Hopefully you understand. It's kind of similar in the time complexity to insertion sorts, because insertion sorts, it compares to all of the left ones. All right, but here you only work with one left one, and then you start again another iteration. So it's kind of similar on the way that we compare the item to the left item. So it's kind of similar in that way, but because we're only comparing 2, we have to make sure that this is also compared. All right, so that's why we take the next neighbors of items. All right, and so on. So it's kind of similar that you do the same again. That's it, guys. Hopefully you understand, and soon we're going to implement this on code. Thank you.